We have a pretty packed schedule, so we should start. So welcome everyone to session 8B. And the first speaker will be John Peoples from Yale, and he will talk about high precision estimation of random walks in small space. So John, go ahead.
Aaron Sidford, and Salil Vadan. We're going to start by talking about the RL versus L problem, which is a problem about what can be computed in a small amount of space. When talking about space usage, we only consider the working memory that
Is it frozen just for me, or?
Can you hear anything?
I can't hear anything. I just heard the first snippet of your talk.
Oh, you did hear that. Okay, it wasn't playing over my speaker for some reason.
This talk is about high precision estimation of random walks in small space. It is joint work with Amir Ahmadinejad, John Kellner, Jack Murtaugh, John Peebles, that's me, Aaron Sidford, and Salil Vadan. We're going to start by talking about the RL versus L problem, which is a problem about what can be computed in a small amount of space. When talking about space usage, we only consider the working memory that the algorithm uses, not the input, output, or random bits, because otherwise the space usage is typically just the maximum of those quantities. RL is then the set of problems that can be computed in randomized logarithmic space with one-sided error. L is the set of problems that can be computed in deterministic log space. The long-standing goal in complexity theory is to show that RL and L are equal. So anything you could compute in randomized log space, you could also compute deterministically in the same amount of space up to constant factors. However, we don't even know how to show that RL and L are approximately equal up to, say, sublogarithmic factors. And this process of trying to take a randomized algorithm and turn it into a deterministic one is called de-randomization. Two methods of attacking RL versus L are pseudorandom generators and graph algorithms. Pseudorandom generators generate a set of sequences that appear random enough that they fool randomized algorithms into still working, even though the sequences were generated deterministically. Unfortunately, current pseudorandom generators require you to generate a large number of sequences in order to find one that works, about into the log n. And if you use that to try to de-randomize log space algorithms, it turns a randomized log space algorithm only into a deterministic log squared n space algorithm. This is using Nissan pseudo-number generator, which is sort of the state of the art. However, if you sort of open this up as a black box, you can actually do a little bit better. You can turn randomized log space algorithms into deterministic log to the 3/2 n space algorithms as a result of Sachs and Joe. And there's been a lot of other work for various special cases in the low space setting. The pros of pseudorandom generators are that they're broadly applicable. They apply not just to low space, but also things like streaming algorithms as well, and they're oblivious to the input of the algorithm. The cons, though, are that they just don't get the space usage that you'd actually want. We want log space here. Another approach is graph algorithms. The way they work is they use the equivalence between randomized algorithms and random walks on directed graphs. It's given by treating each state of the algorithm as a node in the graph and each transition between states or possible transition as an edge in the graph. Then asking questions about randomized algorithms, like whether they accept or reject the input, can be translated into computing questions about random walks in deterministic log space if we want to de-randomize an algorithm. And what's known is that you can compute ST connectivity in undirected graphs in deterministic log space, as well as in Eulerian directed graphs. And it's also known that if you could compute ST connectivity in polynomial time mixing directed graphs, then you could solve any randomized log space problem deterministically. The pros of this are that it gives de-randomization for a lot of natural graph problems, but the cons are that it only estimates the long-term behavior of walks. In fact, for these problems, only just whether it's connected or not even something really quantitative. Our work essentially eliminates this con. We give deterministic roughly log space algorithms for a variety of problems, including finding finite length random walk probabilities, hitting times, commute times, and escape probabilities, all to high precision for random walks in undirected graphs as well as their generalization, Eulerian directed graphs. Our methods combine ideas from the literature on space-bounded de-randomization and nearly linear time Laplacian solvers. In order to explain this line of work we built on, it's helpful to explain what a directed Laplacian matrix is and how you solve them. A directed Laplacian matrix of a graph is a matrix associated with the graph given by the identity matrix I minus the walk matrix of the graph W. Here's an example of one. You don't need to look at it too close. The reason we care about these Laplacian matrices is that being able to perform linear algebraic operations on them is a very useful algorithmic tool to have. In particular, if we could solve Laplacian linear systems, that is, linear systems where the matrix is a Laplacian matrix in deterministic logarithmic space, this would immediately imply that RL equals L very easily. And note that in this low space setting, solving a Laplacian linear system is actually just equivalent to computing the pseudo-inverse of the Laplacian matrix. This is not true in the low time setting, and speaking of the low time setting, solvers for Laplacian linear systems have been a fundamental primitive in algorithmic graph theory, and they've been used for everything from graph sparsification to faster algorithms for max flow and sampling random spanning trees. And the thing that enabled these speedups were nearly linear time randomized algorithms for solving Laplacian linear systems, in particular for solving them in undirected graphs, which is work of Spielman and Tang in 2004. But more recently, we've been able to generalize this to solve it not just in undirected graphs, but to solve Laplacian systems in Eulerian directed graphs. That was work of Cohen, Kellner, myself, Peng, Rao, Sidford, and Vladu, and Cohen, Kellner, King, myself, Peng, Rao, and Sidford. And more generally, arbitrary directed graphs that have polynomial mixing time. This is work of Cohen, Kellner, myself, Peng, Sidford, and Vladu. And sort of analogously to this work, generalizing the classes of graphs for which we can solve Laplacian linear systems in low time, there's been a line of work for solving Laplacian linear systems in low deterministic space. Specifically, in 2017, Murtaugh, Reingold, Sidford, and Vatham showed that you could solve Laplacian linear systems in nearly logarithmic space deterministically. And what this work does is generalizes this to Eulerian directed graphs, sort of giving an analog of that low time result that was previously known. And then you might ask, all right, well, can you then, also extend this to polynomial time mixing directed graphs with no requirement of being Eulerian, as was done in the low time case, and that's still open. The reduction that's used doesn't quite carry over in the low space setting. But if you could do this, you would immediately have RL equals L by that result from that paper we discussed a few slides ago. Applications of being able to solve Laplacian linear systems in a particular class of graphs in nearly logarithmic space include solving a variety of random walk related problems in nearly logarithmic space as well. So things like commute times, hitting times, escape probabilities, estimating mixing times, and whatever class of graphs you can solve Laplacian linear systems in low space in. But the application that we're going to talk about today, which is sort of actually a white box application of our work, is deterministic algorithms for something called EWRP, which stands for estimating random walk probabilities. So what this problem is you're given a random walk matrix W, a natural number k, and an epsilon greater than 0, and you want to compute W to the k, so the kth power of W, to entry-wise error plus or minus epsilon additive. And what we show in our paper is that in space log n k times some polylog stuff, you can compute W to the k for undirected graphs and Eulerian directed graphs. And so here, when we say Eulerian directed graphs, what we mean is that the original graph that the walk matrix W came from, you have it, and it's Eulerian, or undirected. And the approach we use combines ideas from time-efficient randomized Laplacian solvers and from Reingold's theorem, as well as successor works. We don't have time to get into much of the technical content of our paper, but one thing I do want to talk about that's been used in subsequent work is the notion of unit circle approximation, which we introduced. Unit circle approximation is a notion of approximation for Laplacian matrices, and compared to other such notions that have been previously studied, it has the key feature that if we have a walk matrix W tilde and W, and their Laplacian matrices approximate each other, then if we raise W tilde and W to some kth power, their Laplacian matrices still approximate each other, and moreover, this holds with no change in the approximation quality. Prior notions of approximation generally would lose something in the approximation quality if you did this. I'm going to give some intuition now, and in order to do that, instead of talking about a Laplacian matrix I minus W, I want to talk about the number 1 minus W. So we're just going to write 1 minus W, and it's just a positive number that multiplicative approximation for positive numbers, remember, is just defined as, we say, A multiplicatively approximates B within a factor of 1 plus or minus epsilon if the ratio of A and B is between 1 plus epsilon and 1 minus epsilon. And then we want to ask, does this have the key feature that we said above if we stick in 1 minus w and 1 minus w tilde in place of a and b? So we suppose that 1 minus w tilde multiplicatively approximates 1 minus w within a factor of 1 plus or minus epsilon. Remember, these are just numbers. And then we want to ask, how well does 1 minus w tilde squared approximate 1 minus w squared? And the answer, if you work this out, is that it's within a 1 plus or minus 2 epsilon factor. So we are losing something in the approximation quality, and in fact, it's pretty big. Because in more general settings, when we raise w to the kth power, we can lose a factor of k, not just 2. And so we're going to completely wipe out our approximation guarantee if we try to use these existing notions of approximation, which are analogous to multiplicative approximation for positive numbers in the scalar case. That takes us to unit circle approximation. So for positive numbers, our notion of unit circle approximation just says that we require not just that 1 minus w tilde and 1 minus w approximate each other, but that we have approximation for 1 minus zw tilde and 1 minus zw for positive 1 and negative 1 for both those values of z. And this generalizes to not just positive numbers like we've been talking about here, but actually to complex numbers in non-symmetric matrices. And in that case, we require that the approximation hold not just for z equals plus or minus 1, but for all roots of unity. And that's where it gets the name unit circle approximation. And if we do this, we do in fact have the key feature that if w tilde and w, their Laplacian matrices, approximate each other, then the powers of w and w tilde, their Laplacian matrices, still approximate each other with no change in the approximation quality. Our work suggests several future directions. If you could solve not just Eulerian Laplacian systems like we do, but the Laplacians of all polynomial time mixing directed graphs, then you could reduce all of BPL to deterministic log space. And there's reason to be optimistic about this, because in the low time setting, you can reduce this to solving Eulerian graphs. And we solve Eulerian graphs in nearly logarithmic space. So if you could make this reduction run in nearly logarithmic space, then you'd be done. And the question is whether you can estimate high powers of w to the k in nearly linear time. We do it in nearly logarithmic space. Can you get a better understanding of unit circle approximation, which we use? And finally, can you improve or combine our methods with pseudorandom number generators for log space? And in fact, there actually has been subsequent work that has used our definition of unit circle approximation to make progress on it. That concludes the talk. You can find references for most of the papers at the archive link.
Okay, so are there any questions?
I have a question. So can you go over the unit circle approximation slide? So what is the point there? Are you trying to, yeah, I didn't quite catch the point. Can you explain that one again? Yeah,
sure. Okay, so if we have a matrix I minus w, and we want to say it approximates a matrix I minus w tilde, so the sort of existing notions of matrix approximation that have been used, if you specialize everything to just numbers, it's just multiplicative approximation for numbers. And a problem with that is that if we then want to talk about if we have two graphs that approximate each other, and then we want to raise them to some power, so take like a multi-step random walk and still have them approximate each other, when you do that, you lose something in the approximation quality. That's sort of what this slide is saying. And what unit circle approximation does is it removes that issue. You don't actually lose anything in the approximation quality when you go from looking at how well w and w tilde approximate each other to how well their squares or 10th or 100th powers approximate each other. Does that answer your question?
So for a matrix, it's a requirement on the eigenvalues, or?
Not exactly. It's so like I didn't actually write down the definition here, right? Like in the so when you're talking about symmetric matrices approximating each other, the standard definition that's used is you look at the quadratic forms of these matrices and then require that the quadratic forms multiplicatively approximate each other. And quadratic forms, right? They output numbers, so that's multiplicative approximation for numbers is something we already know. And so then if you want to look at these non-symmetric matrices are sort of analogous to complex numbers. And for those, you have to be a little bit more careful in the definition about sort of what it means to multiplicatively approximate for matrices. One definition is that basically normalize things by like sort of a symmetrization, but I don't know if it makes sense to sort of get into the nitty gritty. There's a formal definition in the paper.
Okay, thank you very much. So I guess we're a bit tight for time. So the next speaker, if you can share your slides.
Hi, can you hear me?
Yeah. Okay, great. So so the next talk will be given by Zhongchen Chen on rapid mixing of Glauber dynamics up to uniqueness via contraction. Please go ahead.
Thank you. So I'll talk about rapid mixing of Glauber dynamics up to uniqueness via contraction. And this is joint work with Guigui Liu and Eric Vigoda. So the main topic of this talk is about using a classic MCMC method to sample from a discrete distribution. And I'll first focus on an explicit example, which is the hierarchical model. So the hierarchical model is a distribution over all independent set of a given graph. So we will be given a graph G and a parameter lambda, and the Gibbs distribution of the hierarchical model is a distribution of all independent set of G, where every independent set will have a density that is proportional to a lambda to its size. So if you have single vertex, then it's just lambda, and if it's two vertex, then it's lambda square. And here Z is the normalizing constant called the partition function. And the problem we will study is just to sample from the Gibbs distribution. So we will be given the graph G and the parameter lambda, and our goal is to approximately sample from the Gibbs distribution. And it is known that the problem of approximate sampling is polynomially equivalent to approximate counting, which is compute the partition function Z approximately. And for these two problems, there is a close relationship between to the so-called tree uniqueness threshold, which basically says that when you have small lambda, the parameter is small, then the distribution will satisfy the notion of correlation decay, which means that the correlations between two vertices will decay with their distance. So here I think of every vertex corresponds to a random variable that describes whether it's inside the independent set or not. And for lambda greater than the critical lambda, then even vertices that are far away, they may still have like non-zero correlations. So here is the very more illustrative figure. So the uniqueness threshold is coming from the regular trees, where we consider two scenarios. In the first case, we fixed all the leaves to be inside the independent set. And in the second case, we fix them to be outside. And we consider how the boundaries will influence the distribution of the root. And the uniqueness threshold basically says that when your lambda is small, the influence is zero, goes to zero when you increase the height to infinity. And if it's large lambda, then it's non-zero. And it turns out that for the sampling problem or the counting problem, this threshold is precisely where you have a polynomial time algorithm or MP hardness. So for lambda greater than lambda critical, it is known that there is no polynomial time approximate sampler, assuming some standard complexity assumption like RP is not equal to NP. And meanwhile, for small lambda, there are roughly three types of algorithm. So the first two are by correlation decay or polynomial interpolation, but those algorithms are typically complicated and pretty slow in practice. And the runtime, though it's a polynomial, the exponent of n depends on the degree, capital delta. And in a recent work, actually it's also in this FOCS and it's presented in next talk. So in this new paper, they gave a way to analyze the so-called Glauber dynamics, and they show that the global dynamics is mixes in polynomial time, and the exponent is independent of the maximum degree data. So it's polynomial time even if you have unbounded degree. So let me first introduce what is the global dynamics. So this is perhaps the simplest MCMC method that one can come up with. So in every step of the global dynamics, we will pick a vertex uniformly at random, and then we just update the state of this vertex conditioned on the states of all other vertex. So suppose we pick this one, and we might update it to be occupied. And if we pick this one, then since it already has neighbors to be inside the independent set, so it won't become occupied because of we use the conditional Gibbs distribution. So this is the global dynamics, and we can show that with the correct update rule, it will converge to the Gibbs distribution we want. And the mixing time is defined to be the number of steps it takes to be within epsilon total variation distance from the Gibbs distribution, even when you start from a worst configuration. And so the next talk, the result by Anari, Liu, OVS, Garan, they show that when lambda is smaller than the critical point, the mixing time is polynomial, where the exponent is exponential in 1 over little delta. So here the little delta measures like the gap to the uniqueness threshold. So what we show is that we brought down the exponent from exponential to just linear in 1 over little delta. And how we do this is by we give a better bounds on the spectral independence, which is defined by their results. And moreover, our bounds is a little bit simpler and applicable to other models. So another example where our results apply is the so-called Ising model, which is very well studied. So the Ising model describes the distribution over all 2 colorings of a graph. So usually people use plus or minus to represent the labels or the spins, but I just use the red and blue dots for illustration. So for the Ising model, every configuration will receive a probability density that is proportional to a beta to the number of monochromatic edges. So for example, if you have 4 red vertex, then it's beta to the 4th. And if you have this alternating pattern, then it's just 1 because there's no monochromatic edges. And Z is still the partition function. And also we can see from the definition that when beta is greater than 1, then the Gibbs distribution will favor monochromatic edges. So this is called ferromagnetic or attractive. And when beta is smaller than 1, then adjacent vertex tends to be opposite of each other, and this is called antiferromagnetic. And for the ferromagnetic, it's easier to do the sampling because by a classic result of Jerome and Sinclair, they show that there's always a polynomial time sampler when you have ferromagnetism. And in particular, when the beta is smaller than the critical value, when you have correlation decays, then it mixes in n log n times, which is optimal. And what we show is mainly about the antiferromagnetic Ising model. And we show that when you are in the uniqueness region, the mixing time of the global dynamics is polynomial, where the exponent is linear in 1 over little delta. And this is faster than the other results using correlation decay or polynomial interpolation. And it's polynomial even when the maximum degree is unbounded. And also it's the best region possible because when you are in non-uniqueness, it is known that there is no polynomial time sampler under complexity assumptions. And in fact, our results holds for a general antiferromagnetic 2-spin system. So for general two-spin system, you still have the Gibbs distribution is still for all two labeling of the graph. And you have 3 parameters, beta for the monochromatic red edges and gamma for the blue edges and lambda for the red vertices. So for example, if you have like all red configuration, that's beta to the false and lambda to the false. And if you have 1 red edge, 1 blue edge, that's beta gamma and times lambda squared. And this includes the hierarchical model and the Ising model as special cases, because like, for example, for hierarchical, when beta 0, then the red vertex you won't have adjacent vertex both being red. So all the red vertices will form an independent set. So this is basically the hierarchical model. And so for the general two-spin system, we still have ferromagnetic, which is beta times gamma greater than 1, and antiferromagnetic, which is smaller than 1. And what we mainly show is about the antiferromagnetic case, where the uniqueness is defined by Li, Lu, and Ying, which is a little bit abstract in definition, but it recovers the uniqueness threshold for hardcore and Ising. And what we show is that the mixing time of the global dynamics is polynomial, and the exponent is independent of the degree. So to conclude, we establish rapid mixing of global for two-spin system in the uniqueness region, and also results are obtained for more than 2 spins, in particular for sampling random Q colorings. And finally is an advertisement for our new result, which is the same 3 of us. We actually show that the mixing time of the global dynamics can be n log n, which is optimal in the uniqueness region. And the new paper is also online now. And that's all. Thank you.
Thanks a lot. Are there questions? Can you show again the uniqueness criterion for the general two-spin systems?
Okay. Yeah, so this is the definition of the uniqueness threshold for general two-spin system. So here, this function f is like the tree recursion, which is like how the marginals of the root to its neighbors in the corresponding subtrees, and the threshold is basically saying like the derivative at the fixed point is smaller than 1. So it's kind of contracting from a dynamical point of view.
How does it compare to the usual definition of Gibbs uniqueness?
So one special thing is that this is for the up to delta, where you consider the degree can be you consider all degrees smaller than delta. So I think that might corresponds to uniqueness of all trees of maximum degree smaller than capital delta.
Or it implies it, I guess.
Yes,
it's stronger than that, I guess. Or...
Yes.
I see. Okay.
Yeah, it's stronger than it's stronger than just consider the regular trees of degree delta.
I see. Are there any other questions?
So do you also recover the result on the ferromagnetic regime using your technique?
Yeah, for the Ising model, I think for both for general two-spin system, we also get this result for the ferromagnetic case. But usually for ferromagnetic case, there are better results for globals. So like n to some absolute constants. For example, for Ising, it's known to be n log n.
Okay, thanks very much. Could the next speaker share their slides?
Thank you.
Sorry, one second. Wait, can you hear me?
Yeah.
Okay. Okay, can you see this?
Yeah. Okay, so next we will hear from Kuei Liu, who will talk about spectral independence and high-dimensional expanders.
Okay, hi. So thank you all for coming. I'll be talking about some joint work with Nima Nari and my advisor, Shaina Viskaran. So actually, there'll be some pretty significant overlap between this talk and the previous talk. Basically, in this work, we'll be studying basically the discrete sampling problem. And here, the setting is you're given a non-negative weight function mu on subsets of 1 through n. And your goal is to sample a set S with probability proportional to mu of S. And the main application we'll have in mind is actually it was also mentioned in the previous talk, is the hardcore model. So here the input is you're given a graph G and a parameter lambda. And your goal is to sample a random independent set with probability proportional to lambda to the size of the independent set. Okay. And just to mention that this model is actually extensively studied in the statistical physics literature, and it's been used to model various things such as particles in gas and also communications and networks. So just give one quick example. So let's say we look at the hardcore model on this 3-vertex graph here. And throughout, I'm going to think about independent sets as being sort of the same as coloring all the vertices of the graph red or green, such that the green vertices form an independent set. Okay. And so, we have all these independent sets for this graph here, and they have these corresponding weights. So for instance, this independent set has weight lambda squared because there are 2 vertices colored green. Okay. And if we add them up, we get sort of the normalizing constant for this distribution, and it's also known as the partition function. And it's known that evaluating this partition function exactly is sharply hard even on very restrictive classes of graphs. Okay. So now, as Donjan mentioned in his previous talk, so there's a very natural algorithm based off Markov chains, which is called the Glauber dynamics. And basically what you do is you sort of collect all of your independent sets, and then you endow this state space with a neighborhood relation. Basically, you say that, at least for the Glauber dynamics, a very natural neighborhood relation is to say that 2 independent sets are neighbors of each other if they differ in the status of exactly 1 vertex. Okay. And then, so now you can think of this as basically a graph on all independent sets. And then now you can just run random walks. So the Glauber dynamics basically does the following. At each step, what you do is you pick a uniformly random vertex, and then you resample the color of that vertex conditioned on the colors of all the other vertices in the graph. Okay. Okay, so now we define the mixing time as just being the first time t such that the distribution of the Markov chain is close to the desired distribution in total variation distance. And the question is well, when is this mixing time bounded by a polynomial in the size of the graph? Okay, polynomial in n. Okay, so it was known for a long time that basically there's this critical threshold that Zhongshan also mentioned, that lambda c of delta, where delta is the maximum degree of the graph, it is roughly e over delta. And this critical threshold delineates between when you have hardness results and when you have efficient algorithms. So basically for lambda below this critical threshold, we expect the Glauber dynamics to be rapidly mixing. And then for lambda above this critical threshold, you cannot hope to have efficient approximation algorithms. Okay. So at least regarding Glauber dynamics, the problem of using the Glauber dynamics to sample from the hardcore model was first studied in this work by Luby and Vagoda in the 90s, who showed that for lambda below 1 over delta minus 3, you can get fast mixing. And then over the years, this was gradually improved all the way to actually get up to this critical threshold under further structural assumptions on the graph, such as large degree, large girth, or sub-exponential volume growth. Okay, but prior to our work, the best known result for general graphs of degree at most delta required lambda to be at most 2 over delta minus 2. Okay. On the hardness side, it was already known to Luby and Magoda in the 90s that for lambda above some constant over delta, it should be NP hard to approximate the partition function efficiently. And this constant was gradually reduced all the way down to this critical threshold. And finally, sort of in this breakthrough work by Alan Sly and also in many follow-up works, they managed to show this they managed to get it to the critical threshold. Okay. So now let me sort of be a little bit more precise about this complexity phase transition. What Sly and follow-up works showed is that for lambda above this critical threshold, there's no efficient algorithm for estimating this partition function unless P equals NP, basically. And using like very well-known connections between approximate sampling and approximate counting, this also means that there's no efficient sampling algorithm, basically. And sort of on the positive side of things, actually, in this also another breakthrough work by Dror Weitz in 2006, he showed that for lambda below the critical threshold, there does exist a deterministic approximation algorithm for this partition function, and its running time scales as exponentially in log of the maximum degree and in 1 over little delta, which is how close you are to the critical threshold. Okay. So now there are basically two main drawbacks behind this result. First is the exponential dependence in log of the maximum degree. So this is in particular not efficient for graphs with unbounded degree. And I guess the second is that, as in my opinion, this algorithm is significantly more complicated to implement compared to the Glauber dynamics. Okay. So what we showed in this work is that for lambda below this critical threshold, we actually do get rapid mixing of the Glauber dynamics, and we don't need to make any additional structural assumptions in the graph, and we avoid this exponential dependence on log of the maximum degree. Okay. And then as Sungchun said in the previous talk, in this follow-up work, we managed to get this down to n to the 1 over little delta as compared to doubly exponential in 1 over little delta. And then let me also mention that, so the techniques that we introduced in this work have since been extended to allow sampling proper colorings on triangle-free graphs. Okay, so now let me describe some of our techniques. So the first thing we do is we introduce this notion called spectral independence. And to define it, we define this sort of pairwise influence matrix of the distribution mu. Okay, so it's an n by n matrix. It's in general asymmetric, and its entries are given by this difference of conditional marginal probabilities. Okay, so basically, you should think of this as being the influence of the element j on the element I, because this is really asking, well, how does the status of j, being in or out of the random set S that's sampled from mu, how does the status of j affect the marginal probability of I being in the set S? So this is like an influence. And then we say that our distribution is spectrally independent if actually this maximum eigenvalue is bounded. Okay, so let me just show you two quick examples. So the first is that if mu is a product distribution, then these two conditional marginal probabilities, well, basically you should think of that the element I and the element j are independent of each other. And so these two conditional marginal probabilities are the same. And so the difference is 0. And so basically what we're saying is that if mu is a product distribution, then the influence matrix is a 0 matrix. And sort of at the other extreme, if let's say we have mu is supported on just these two sets, they're disjoint of each other, then basically if I know the status of one element, then I actually know the status of all the elements, right? If I know 1 is in the random set S that I sample from mu, then I know that I sampled the purple set. And that means that all these elements are in and all of these elements are out. And so in this case, you can show that the influence matrix is this matrix of basically +1s and -1s. And then you can compute its eigenvalues explicitly. It has a very large maximum eigenvalue. Its maximum eigenvalue is n-1 actually. So these are sort of the two extremes. Okay. And then, so now the next thing we need to do is to actually need to strengthen this definition to encompass all of the conditional distributions of mu. Okay, and basically our main technical result, which applies to all distributions, not just to the hardcore model, we show is that if not only is the distribution alpha spectrally independent, but all of its conditional distributions are alpha spectrally independent, then the Glauber dynamics for sampling from mu has n to the minus alpha spectral gap. Okay, and so you should think that for polynomial time approximation algorithms, you want alpha to be a constant independent of n. Okay, and so basically to get our result for hardcore, what we show is that for lambda below this critical threshold, we can get spectral independence with a constant independent of n, but depending on this gap parameter delta. Okay, so combining these two results, we get our mixing result for the hardcore model. Okay, so in the interest of time, I'm just going to briefly outline the strategy that we take in this work. So what we want to get is the rapid mixing of the Glauber dynamics. So using very recent and very exciting developments in the area of high-dimensional expanders, we reduced this to a problem of obtaining spectral expansion of exponentially many local random walks. So these local random walks are local in the sense that the entries of these random walks are basically these conditional marginal probabilities. And there will be a random walk for every conditional distribution mean. And I'm not going to define what it really is. So in this work, what we show is that if you have spectral independence, basically a bound on this influence matrix, then this implies very strong spectral expansion of these local random walks. Okay? And then finally, what we do is we use, to obtain spectral independence, we use this method of correlation decay, which was also used by Georg Leitz to obtain his deterministic approximation algorithm. So basically what correlation decay says is that this influence matrix has a very nice structure. Basically for vertices that are very far from each other, the influence of these two vertices on each other is very small. It's in fact exponentially small in their distance. Okay, and so basically you use this property, basically bounds on the entries of this influence matrix to obtain a bound on its maximum eigenvalue. Okay, and so now let me just conclude with just some future directions. So first, can you find new applications of these techniques? For instance, can you improve current sampling results for proper colorings, or to obtain sampling algorithms for common basis of two matroids? And the second question is can you find new methods to certify the spectral expansion of these local random walks? Okay, and I'll stop here. Thanks.
Thank you. Are there questions? Maybe if you, oh, sorry, go ahead. Yeah.
So it seems like your definition of spectral independence, at least the basic version, is some notion of approximate pairwise independence, the basic one, and then I guess with all the other conditions, it maybe is capturing some kind of approximate k-wise independence, or one maybe can formulate some kind of approximate k-wise independence in this way. So I'm wondering, from a kind of a pseudo-randomness perspective, could potentially these be substitutes and maybe ones that are for kind of other uses of pairwise or k-wise independence in de-randomization and other places where we use those notions? Can maybe they be we have spectrally independent distributions that are generated with fewer random bits than we would need for the corresponding notion of k-wise independence?
Okay, that's a very interesting question. I haven't really thought about it, but I guess yeah, it is. If you have something like k-wise independence, it's very nice because then the influence matrix is just 0 for many of the. I guess if it's pairwise independence, the influence matrix is 0. If you have k-wise independence, then a lot of its conditional distributions are also have influence matrix 0, and I guess yeah, I haven't really thought about it, but it does seem like a very nice direction to think about. Yeah.
Thanks.
I just have a quick question. The connection between the correlation decay and the matrix, so the last arrow on the right, this relies on it being a regular graph, or that's not important?
It doesn't need to be regular. I'm hiding a lot of technical details here, but this is like roughly speaking what needs to happen. Yeah.
Okay, thanks. So can the next speaker share their slides?
Yeah, can you hear me and see the slides?
Yes. Okay, so next we'll hear from Michał Dzerzynski on isotropy and Log-concave polynomials.
Thank you. So I'm a postdoc at UC Berkeley, and this is joint work with Nima and Ari at Stanford University. Yeah, so the basic problem here is again, sampling from discrete distributions. We're given Hierarchical access to a distribution over subsets of size k over a ground set of n elements, and our goal is to approximately sample from it. And so of course, we're using this as a canonical form, which is motivated by many specific examples of discrete sampling. In particular, we consider settings where the ground set n is much larger than the size of the output set k. And so we're asking, when can we sample from mu in time that is polynomial in the output size k? So of course, in general, this is impossible because, well, we must at least observe all n elements of the ground set. But in fact, we show that after some pre-processing, we can actually achieve this goal of poly-k sampling for a wide range of distributions. So a useful analogy here is in sampling from continuous distributions, such as, for example, random walks over convex bodies, where a key concept is isotropy. So essentially, we can think of a density function f being in isotropic position when it's essentially all directions in the high dimensional space are equally important. And a very sort of powerful framework for showing that random walks are sort of fast mixing for sort of continuous distributions is establishing that the density function is in isotropic position and that it is a log-concave function, which just sort of ensures that it's sufficiently well behaved. And in fact, instead of requiring that the density be in isotropic position, we can also often transform it to isotropic position by a affine transformation. So our goal is to sort of obtain an analogous framework for discrete distributions. And the key missing component so far has been the notion of isotropy. So the notion of isotropy that we propose for discrete distributions, so now here we're again sampling over subsets from a ground set of n elements. And so here isotropy for us means that all elements of the ground set are roughly equally important for sampling from mu, which for us means that the marginals are the same or nearly the same, the marginal probabilities of each element. And here again, if we know the marginals of a distribution mu that may not be isotropic, then it turns out it's relatively easy to convert it to isotropic positions. So conceptually, you can think of this as sort of duplicating elements proportionally to their marginals, sort of to achieve that transformation. So with this sort of notion of isotropy defined, we can state the main results. So given hierarchical access to this distribution mu that is nearly isotropic and has a log-concave generating polynomial. So this is analogous to the log-concave density for continuous distributions. So then we can approximately sample from mu in poly-k time, right, where k is the output set size. And the second main result is that, in fact, we can also, for any mu with a log-concave generating polynomial, which may not be isotropic, we can convert it to nearly isotropic position in time n times poly k log n. So there's a little bit of background here on log-concave generating polynomials. I'm not going to go into the details, but I mean, this covers a wide range of sampling distributions, including determinant top point processes, sampling over a matroid basis, or specific examples like random spanning trees and forests and such. Sampling from distributions with a log-concave generating polynomial in polynomial time has already been established. in a work by Anari, Liu, Ovisgaran, and Vincent. And it's achieved by a very simple random walk, which runs in time n times poly k, which sort of can takes poly k steps to mix, but overall runtime is n times poly k. And so I will refer to this as the down-up walk. It's essentially based on sort of maintaining a subset of size k and then appropriately randomly swapping one element at a time. But crucially for us, there is still a dependence on n in the runtime, which we would like to avoid. So an important class of these distributions that is worth mentioning here is that I mentioned earlier is determinantal point processes, and this is relevant here because in our work we use some of the ideas that I used in my prior work for sampling from DPPs. So here a natural way of defining this distribution is by associating each element of the ground set by a vector, and a probability of a set is being proportional to a volume spanned by those vectors in an appropriate space. And so an example is random spanning trees, but these distributions found applications in various applications in machine learning and statistics. And my favorite one is there's a range of applications, sort of theoretical guarantees for randomized numerical linear algebra, and such as for least squares and matrix reconstruction type problems. So my prior work on sampling from DPPs, together with Calandriel and Valco, we essentially answered the question posed at the beginning, showing that if mu is a DPP, then we can convert it to nearly isotropic position in n times poly k log n time, and then sample in poly k time. And in fact, we can sample exactly in the case of DPPs. And the idea behind this, which I call the distortion-free intermediate sampling, this is very simple. So we have our ground set n, ground set of size n, and then we're going to generate an intermediate sample of size larger than the target size, intermediate sample sigma, which is going to be of size poly k, and then we're going to downsample from that using the distribution mu restricted to the intermediate sample. So the fact that now so we can think of the intermediate sample as something that's easy to generate, like uniform sampling. And then this reduces the size of the ground set significantly so that the second stage can be more efficient. So the fact that we can actually do this in a distortion-free way, so that relies on specific properties of determinantal point processes, which do not translate to general distributions with log-concave generating polynomials. So the question we had was, can we extend this intermediate sampling paradigm to this general framework, but with approximate sampling? And so the answer is yes. And the basic idea here is we're sort of converting this intermediate sampling to something that we call an instantly mixing random walk. So here's what I mean. So again, we start with some, so this is a random walk. So we start with at some set of size k as 0. Then we we sort of sample a collection of additional elements from the ground set, larger collection, and then we merge them together, the S0 and the additional elements. And then we use this as the intermediate sample to downsample via mu that is restricted to the intermediate sample. So it turns out this random walk has mu as its stationary distribution. And if the intermediate sample is sufficiently large, is at least k squared size, then it mixes instantly, which what I mean by that is that already after one step, the total variation distance, it achieves like fractional total variation distance from mu. And so it gets epsilon close in log 1 over epsilon steps. And the remaining piece is how do we sample from the mu restricted to sigma, and this can be done sort of by introducing this sort of notion of a hierarchical walk, where we have sort of the macro steps of the instantly mixing walk, and then we sample from the mu restricted to sigma using the down up walk that I mentioned earlier, which is running only on the ground set that is restricted to sigma, and which is why it achieves a poly-k running time. So to conclude, I show so one sort of motivating application of this for counting bases over rank k matrix to epsilon relative error in time n plus 1 over epsilon squared, as opposed to n over epsilon squared, which means that we can count to much higher precision in nearly linear time. And I would say the main conclusion here is that this concept of isotropy turns out to be useful for not only continuous, but also discrete distributions. And there's a number of open questions. In particular, we expect that it is possible to sort of extend the ideas of isotropy as well as intermediate sampling to beyond distributions with log-concave generating polynomials. So this is an interesting future direction. Thank you.
Thank you. Are there any questions? Maybe you can first comment a bit more what you mean by higher order marginals, this last point.
Sure. I guess so the notion of isotropy that we're using is based on marginals of individual elements, right? So that there's this transformation that happens to get to nearly isotropic position. So so the idea here is maybe sort of looking at one way to go beyond this is to look at, say, marginals of all pairs of elements, and then transform the distribution to sort of try to uniformize those marginals to a certain degree. And that's sort of a possible approach of trying to go beyond sort of log-concave generating polynomials here.
I see. Are there other questions?
So can this be viewed as some sort of isotropy provides some sort of warm start? Is that a possible message here?
So I mean, I think that could be a good intuition. It's sort of I guess the isotropy here sort of ensures that yeah, I guess we don't have to. I guess you could say that normally we'd have the initial phase of sort of exploring to find the elements with the sort of high marginal probability, right? So we sort of avoid that here, and this warm start comes in the like a pre-processing stage where we convert to the isotropic position. So I guess you could say that yeah, and in fact we sort of have something like this. We have this sort of cooling schedule for gradually finding this isotropic position, which is sort of like this this exploration phase, I guess you could say. For so that's I didn't cover that in detail, but that's essentially the second result, right, which shows how to convert to isotropic position in n times poly-k time.
Thank you.
Okay, thanks a lot. Could the next speaker share their slides? Okay, so next we'll hear from Andreas Galanis on the complexity of approximating averages on bounded degree graphs.
So hello everyone, this is joint work with Daniel Stefankovich and Eric Vigoda. So yeah, we all know that finding an independent set of maximum sizes is an NP-hard problem. So in this talk, we'll focus about finding the average size of independent sets. So again, it will be more instructive as in previous talks earlier in the session. It will be more instructive to look at the weighted version of the problem, the hardcore model with parameter lambda. So given a graph G, we'll look at the set of independent sets of G. And for an independent set, the weight in the Gibbs distribution is lambda is proportional to lambda raised to the size of the independent set. And we look at the aggregate size of all independent sets, which is known as the partition function. So what we will be interested in is the average size of the independent set. So we sample sigma independent set according to mu, and we'll look at its expected size. So in particular, for lambda equals 1, we obtain the unweighted version of the problem, which is just the average independent set size. And the general context here is basically, can we compute averages in Gibbs distributions? There is a well-developed theory for computing partition functions based on phase transition, but not actually for averages. So let's see what's different. Even actually for the exact counting problem, it was only established very recently by a few years ago that exact computation is number p-hard on bounded degree graphs. And what we will focus is for which lambda we can approximate the magnetization. So previous algorithmic hardness results are for the partition function, and the key is whether parameters line uniqueness versus non-uniqueness. So I will explain briefly what that means, but the idea is that there is a critical threshold such that when lambda is below the critical threshold, then you have an approximation argument for the partition functions for all graphs with maximum degree delta. And this, using standard result, actually implies an FP task for the magnetization. So there is standard self-reducibility results that allow you to do that. Now, above that threshold, the critical threshold, it's NP-hard to approximate the partition function with the regular graphs. And interestingly, that does not imply hardness for magnetization. So, actually, that's no coincidence. So there is a good reason for that. There is no general reduction from approximating averages to approximate counting. And the actual previous hardness results techniques do not apply. So our main contribution is bridge that gap. So we saw that it's NP-hard to approximate the magnetization on graph G on maximum degree delta. And we saw almost constant factor in approximability results. So for all lambda in the non-uniqueness region, for all lambda above that critical threshold. So it's theta 1 over log n there, 1 plus minus theta 1 over log n. And actually we can bootstrap that to constant factor in approximability for a dense set of lambda. In particular, if you are wanting for the unweighted case, it is for lambda equals 1, that's a constant factor that has constant factor in approximability as a corollary of our techniques. And this result is optimal. So in the complementary regime, you have an approximation algorithm. So our results apply more general for general ferromagnetic two-spin models. And the key contribution is we introduce a new reduction technique to study the problem. So I will briefly say it's trees with same occupancy ratio, but different derivatives. So I will go a bit into what were the previous techniques and why we need to amend them. All right, so first of all, let's start with the phase transition of the delta regular tree. So we look at delta regular trees of height h, and we look at the relative weight of independent sets that include the root. So we look at this probability, the occupancy ratio of the root as h goes to infinity. And what you see is an oscillating behavior between even and odd levels. And that behavior persists for lambda above the uniqueness threshold. So to get hardness out of that, and to get an approximability result from non-uniqueness, actually one has to work much harder and consider much more complicated graphs. And the key here is to consider bipartite random delta regular bipartite graphs so that you can see this even versus odd oscillating behavior. In particular, what this gadget also undergo a phase transition at the same uniqueness threshold. And what has been shown in a series of works is basically that an independent set sampled from the Gibbs distribution is with high probability unbalanced. So you sample an independent set, it has more vertices on one side versus the other. So what you can define is you can define the phase of an independent set. It's plus if side plus has more vertices and minus otherwise. And you can show that the phases appear with a roughly equal probability. And happily, this was hard work, but it has all been done. So how to use that then in reductions. Well, and that's also quite a very clever reduction. So basically, one needs to use these bipartite gadgets to reduce from max cut. So the idea is you have an instance of max cut and you replace each vertex of the gadget, each vertex of the graph with a distinct copy of the gadget. And you make appropriate connections. Now the key idea is that if you do the connections in a smart way, neighboring gadgets prefer to have opposite phases. So you sample an independent set from this final graph. Neighboring gadgets prefer to have independent opposite phases. And what that allows this to do is basically you can interpret the phases for the gadgets as a cut of the graph. So neighboring gadgets are more likely to have opposite gadgets. The maximum likelihood gadget phase configuration corresponds to a max cut assignment. And more concretely, you can show that if you look at the logarithm of the partition function of this graph, of the final graph relative to the partition function of the gadget, it gives you an approximation to max cut. And there are lots of calculations that need to be established to establish that, and you need to power the gadgets and so forth. But that's the rough idea. Okay, so that looks promising. Let's do the same thing. What goes wrong, right? So what happens for magnetization? Okay, so basically magnetization is linear, right? So you can decompose into two parts, the gray part and the yellow part. And the gray part is, the main portion of the gadget, and the yellow part is where you make the connection between the gadgets. And where the max cut value shows up is in this, in the magnetization of the yellow vertices. And you can show something, again, very roughly, that is roughly a constant times the max cut of the original graph H. And now what causes huge problems is actually figuring what is the expected magnetization of the gray vertices on these random bipartite gadgets. So their analysis requires very refined techniques even for the partition function. It turns out actually that for magnetization, you need to understand the effect from condition on the terminal. So the only reasonable way to analyze these gadgets is basically to condition on the yellow vertices so that they are disconnected from the rest of the graph, and then find the expected value of the gray vertices of the main portion. And this requires very refined estimates, and it gets, so you only have access through moment calculations, basically. And yeah, it's not known how to do that. So yeah, so our main reduction idea is basically to understand this effect of conditioning for much simpler gadgets, trees, right? So you don't want to mess with complicated graphs. Trees are the best thing that you can hope for. So let's see, what's the new gadget? It's a field gadget. We call it field gadget, which is a cubic tree, right? Degree maximum degree 3, and the degree of the root is equal to 1. Now we studied two relevant quantities, the occupancy ratio as before, as for the delta regular tree, but also we look at the so-called magnetization gap, and the magnetization gap captures this effect of conditioning, right, at the root. So whether the root belongs to the independent set or not. Okay, so how do we use these field gadgets? Let's think about it. Well, you don't do much. Instead of appending, having simple edges, you now append these trees on each set separately. Okay, and the idea is again a linearity of expectation. Magnetization you can now decompose in 3 parts: gray, yellow, and purple. And again, the value of the max cut shows up in the value for the purple magnetization. And you can show that the magnetization gap of the field gadget shows up in the purple vertices. So that's why it's relevant magnetization gap. Okay, so now, but again, we are in the same situation, it seems, right? How can we get rid of the gray and yellow vertices? We still can't compute those, right? But now you have freedom to choose your field gadget, right? So you have the freedom to change the field gadget. And if you do it in the following way, you can do something. So the idea is to find 2 field gadgets with the same occupancy ratio and different magnetization gaps. And the point is that the distribution, because they have the same occupancy ratio, the distribution they induce is the same. And in particular, the magnetization of the gray and yellow vertices are going to be the same when you do the reduction. So the idea is you look at the magnetization of the 2 final constructed graphs for T1 and T2 under the 2 field gadgets, and these expectations nicely cancel out, and you get the max cut. And this avoids basically having to argue to find these very refined estimates for the expected value of the gadget. Okay, so what's the main idea then? Well, we need to find these pairs of trees, right, with the same occupancy ratio but different magnetization gaps. So how do you do that? Well, that's the main part of the main and hard part of the paper. But for independent sets, I can give you the trees explicitly, right? So these are the two trees, right, for lambda equals 1. Okay, and that proves basically, according to these lines, the inapproximability result. Now, to get the result for general lambda, it turns out that you cannot hope to do this kind of constructions for all lambda, right? So you cannot match. If you think about it, you can only prove it for. You can only hope to match this for a countable set of lambda. Okay, so what do you do instead? You obtain approximation, right? So you almost match them. You almost match all the occupancy ratio, but you guarantee the magnetization gaps are different by a constant. And yeah, it turns out that this is actually challenging. So magnetization, even on trees, it's also hard to control, and it requires various ideas from previous paper. And the final construction, actually, you need to argue by Cauchy's functional equation to establish the existence of the gadgets. But actually, once you do that, we can actually control the size of the gadgets and gives this refined approximation factor of θ1 over log n. And because you can interpret these things as derivatives, you can actually ensure that you can actually match up the occupancy ratios for a dense set of values. So I will stop here. That's our main results. General ferromagnetic two-spin and NP hardness result for approximating magnetization in non-uniqueness. Thank you.
Thank you. Are there any questions? Can you show the main technical result on the previous slide? So this holds for every lambda. For this, it doesn't matter if lambda is in the uniqueness regime.
So non-uniqueness is needed for the gadgets, the bipartite gadgets, but for that one you can do it for every lambda. So yeah.
I see.
It's a bit surprising, but yeah, initially that's right. But the idea is that the point where you construct these gadgets is actually at the at the translation invariant fixed point. So it doesn't matter whether you're in uniqueness or in non-uniqueness. So yeah, it's.
I see. And when you use this argument via the Cauchy's functional equation, this involves the tree recursion, right? So even there, the lambda being in uniqueness or non-uniqueness, it just doesn't show up.
That's right. It doesn't show up. It doesn't show at all. That's right. I mean, it's harder to do the gadgets in non-uniqueness, but yeah, it's the analysis works throughout for all lambda bigger than 0.
I see. Okay, that's surprising. Are there other questions? Can you comment a bit on the idea of the construction? I know it's like an iterative construction.
Oh yeah, so yeah, basically you have 2 trees, you can combine them into single trees, right? And that's the function that you have basically, right? So you combine the messages, and that's the occupancy ratio that you get and the magnetization gap. So occupancy ratios are well studied. So the way that you can construct such trees that converge to some occupancy ratio is you look at the fixed point of the 3 recursions. So you look at what happens on the 3 regular tree, and you construct these field gadgets with whose occupancy ratios are particularly close to P star. And that uses earlier construction, but we have to generalize that. And once you have that, you can actually bootstrap because you have convergence properties actually close to that you can establish. So you can construct first, a few ratios close to that fixed point, and then you can start combining them, and actually it gives you a very fast convergence to P star. Okay, and once you have that, you need to control what happens for magnetization, and basically you consider a lot of sequences of these trees, many sequences, and yeah. So if you find the sequence that has different magnetization gaps, you're happy, basically, and you're done. If you're not, what you can show is that for every point that you wish to achieve occupancy ratio, you can actually define a function that gives you the magnetization gap. And basically what you do for that function, you prove that it's continuous. And there you use basically that you have all those many trees that converge to the same value. And you can write basically a Cauchy functional equation that gives you, that the gadgets should satisfy some property if you want this function to be well defined, and it cannot happen basically. And yeah, various leftover details, but that's the very rough idea.
Okay, thanks so much. Then I think we have one more speaker, so can you please share your slides?
Yes, 1 second. Okay, can you see that?
Yeah. Okay, so the last talk will be from Mark Roth on counting small induced subgraphs satisfying monotone properties. Please go ahead.
Yeah, thank you everyone for attending this very last talk. This is, as Nike said, about counting induced subgraphs, and this is joint work with Johannes Schmidt and with Philipp Wellnitz. We're actually interested in counting small induced subgraphs that satisfy some given graph property. So let me define it formally. So given a graph property phi, a positive integer k, and a graph g, then in sub phi k to g is defined to be just the set of all induced subgraphs of size k in the graph g that satisfy phi. Let's consider the following easy example. So let this be our graph, let phi be bipartite and let k be 4. Then those two are bipartite, induced and of size 4, and those two are not. And yeah, we will be interested in the complexity of computing the cardinality of this set. So let me define the function sharp in sub phi k to star as the function that expects as input a graph g and then outputs the number of induced subgraphs of size k in g that satisfy phi. And this family of functions here is very general. You can encode many different counting problems that have been studied before by just inserting appropriate graph property phi. And unsurprisingly, we are not the first ones to study this problem. It was originally introduced by Jeremy Meeks a couple of years ago. And yeah, we will be interested in the complexity of exactly computing this function depending on the graph property phi. And let me model the complexity of this function by the so-called complexity exponent due to Kote-Kapi, Andel, and Marx. So given a function from graphs to rationals f, I define the complexity exponent of f as the infimum over all c, such that you can solve f in time number of vertices of the input graph to the c. And yeah, let's just consider some easy examples for properties and for the complexity exponent. So if this property is constant, true or false, then computing this function is trivial because you either output 0 if it's false, or you output number of vertices of your input graph, choose k. And then depending on the encoding of your graph, the exponent is either 1 or 2. The brute force algorithm for this problem just iterates over all tuples of over all k tuples of vertices of the graph, and then computes how many of those tuples satisfy induce a graph that satisfy the property. So for any computable property phi, the complexity exponent is always upper bounded by k. And then we ask the question, for which properties phi can we actually beat the brute force algorithm? And yeah, quite unfortunately, in a quite long line of research, it was shown that for many properties, you can actually not improve upon the brute force algorithm, at least not significantly. Of course, this lower bound here is a conditional lower bound. It assumes the exponential time hypothesis. And yeah, we actually assume that whenever you have a non-trivial property phi, you cannot solve this problem significantly faster than brute force unless the ETH is wrong. And you have to be a bit careful with your definition of non-triviality here. So a property that eventually becomes true or false if k grows is not non-trivial in the usual sense, but this will not be an interesting property. So, but for every like interesting non-trivial property like connectivity, we actually assume that you cannot significantly beat the brute force algorithm. And in this work, we proved a weaker version of this conjecture for monotone properties. That is, we showed that the complexity exponent of computing this function is not in small o of k over square root log k whenever phi is a non-trivial graph property that is monotone. And by monotone, I mean here closed undertaking of subgraphs. Examples are the property of being bipartite or three-colorable. And furthermore, we proved the same conditional lower bound for properties that are non-trivial and only depend on the number of edges of a graph. And the second one actually proves conjecture, an older conjecture by Jerem and Meeks. So that was what we did. Let me at least sketch the important ideas how we could prove this result. And yeah, we used the tool called graph motive parameters by Kutikapi and Dell and Marx. So let me give a very rough introduction. A graph parameter f is a so-called graph motive parameter if it is equivalent to a finite linear combination of graph homomorphism counts. That is, f is expressible, so there need to exist a finite number of coefficients ai and graphs hi, such that f is equal to the function that expects as input a graph g and then outputs the evaluation of this linear combination. This notation here, sharp hom hi to g, is the number of graph homomorphisms from hi to g. I won't formally define what a graph homomorphism is. It's just an edge preserving mapping from the vertices of hi to the vertices of g. And the reason why those graph motive parameters are useful is the so-called complexity monotonicity principle, stating that the complexity exponent of a graph motive parameter is equal to the maximum of the complexity exponents of the homomorphism counts. Roughly, this means whenever you want to compute a finite linear combination of graph homomorphism counts, this is precisely as hard as computing its hardest term. And you don't get this property for any linear combination of counting problems. This is really a very special property that holds for counting homomorphisms. And now this leads to the question how hard it is to compute graph homomorphisms. And fortunately, this is already very well understood. So computing the number of graph homomorphisms from a graph H can be done from a graph H to a graph G can be done in the number of vertices of G to the tree width of H plus 1 by a dynamic programming algorithm over the tree decomposition due to Diaz et al. And Marx showed that assuming the exponential time hypothesis, you cannot be better than small o of tree width of H over log of tree width of H. And actually the question whether you can get rid of this 1 over log of tree width of H factor is referred to as can you beat tree width? And this is one of the major open problems here. Okay, yeah, I won't define tree width formally, just think of it as being a measure how tree-like a graph is. So trees have pretty small tree width 1, and cliques have very bad tree width. Okay, and yeah, to sum it up, so counting the number of homomorphisms from a fixed graph H is the complexity of that problem is really given by the tree width of the graph H. And now how can we apply this to our problem of counting induced subgraphs? And now, yeah, they are 3 quite easy steps. So in the first step, we have to prove that we can actually express this function of computing the number of induced subgraphs as such a finite linear combination of homomorphism counts. The first step is only a proof of existence. We, of course, also need to determine which of the coefficients in this linear combination are non-zero. And then we are done, because then we can just insert complexity monotonicity and get that the complexity of counting the number of induced subgraphs of size k that satisfy phi is precisely as hard as counting the number of homomorphisms from the hardest term in this linear combination. And this might be surprising at first glance. It certainly was for me. The first step is actually the very easy one. So those transformation, proving this, just that such a transformation exists, is pretty easy. It usually follows just by inclusion-exclusion or by Möbius inversion. But the very hard part is to find out which of those coefficients actually survive this expression as graph motive parameter. Because you have to collect for isomorphic graphs HI, and it could be that those coefficients just cancel out. So you really need to find out which of them are 0 and which of them are non-zero. And in this work for monotone properties, we solved this by considering so-called F and H vectors of graph properties. They generalize the equivalent notion of simplicial complexes. Let me give the definition. This may seem rather technical, but it's actually quite simple. So given phi and k, the ith entry of the F vector of phi and k is just the number of the edge subsets of the clique of size k, such that the number of edges is I, and the induced graph satisfies phi. And you probably believe me that if phi and k are given, then it's usually very easy to determine whether an entry in this vector is 0 or non-zero. On the other hand, the H vector is this transformation of the F vector, and here it is much harder to see which entries of the H vector are 0 or non-zero because it's an alternating sum. And our technical main result states that this H vector actually almost completely determines the complexity of computing induced subgraphs of size k that satisfy phi. So let me state this theorem. So given given phi and k, we can prove that there are those unique rationals A1 and AL and graphs H1 to HL, such that you can express the function sharp in sub phi k as a finite linear combination of homomorphisms with respect to those coefficients and those graphs. And again, this is the easy part, and it was known before, but the harder thing, the important thing is that we could prove that for all indices j, if we take the sum over all I, such that the graph hi in here has k vertices and j edges, then take the coefficient in I, then this is precisely equal to the jth entry of the H vector times k factorial to the -1. And why is this useful? We get as a corollary that whenever we have an whenever the H vector has an index, a high index non-zero entry, then a graph with high tree width must survive in the graph motive parameter expression. And very roughly, the reason is that, okay, if Hj is non-zero for some j, then for some high j, then there will be a graph with many edges surviving in here. And if a graph has many edges, then the tree width of the graph will be high, very roughly speaking. Now, how can we use this result? So we call that, yeah, it's actually quite hard to see whether entries of the H vector are 0 or non-zero. And we could relate the H and the F vector by the so-called F polynomial, which is also a generalization from simplicial complexes. I won't define the polynomial, just state the two important facts. So the k choose 2 minus ith derivation of the F polynomial in 0 is the ith entry of the F vector. And the k choose 2 minus jth derivation of the F polynomial in -1 is the jth entry of the H vector up to j factorial. And using this, we could apply Hermite-Birkhoff interpolation to show that whenever the F vector has small Hamming rate, then the H vector contains a high indexed non-zero entry. And if you don't know what Hermite-Birkhoff interpolation is, just think of it as being a variation of polynomial interpolation where you also can use constraints on the derivations of the polynomial. And yeah, then collecting for what we have seen so far, I can state a quite restricted and informal version of our main result, stating that whenever the F vector of a graph property phi and k has small Hamming rate for infinitely many k, then the complexity exponent of computing the number of induced subgraphs of size k in the graph that satisfy phi is not bounded by a constant unless ETH fails. And this is, of course, weaker than the results I showed you before, but you can get the stronger lower bounds if you just take an even closer look to the correspondence of the F and the H vector. But even this result here shows that if k is part of the input, then you don't get a polynomial time algorithm, and you don't even get a fixed parameter tractable algorithm if you parameterize by k. And this means that having an F vector with many zero entries really shows that this problem becomes very hard. That was everything I can show you in this short amount of time. Thank you very much.
Thank you. Are there questions? Can you maybe discuss some future directions or open problems that this suggests?
Yes, so the major open problem would be whether you can prove this not only for, let me go back to this slide, whether you can prove something like this not only for monotone properties, but for all non-trivial properties. And this seems to be quite far away, but a first step could be to consider just properties that are closed under the removal of edges only, that is edge monotone properties. Connectivity is, for example, on being not connected is a property that is closed under the removal of edges only, for example, but it's not closed under taking also under removal of vertices. So we actually are currently trying to prove this first result here also for edge monotone properties, but even for edge monotone properties, it seems to be much harder, because then, at least if you use the technique in this work, you won't get many zero entries in the F vector. But yes, as a concrete open problem in this field would be to consider edge monotone properties and prove that whenever they are non-trivial, you get hardness.
And what about if instead of, or if in addition to monotonicity, you have some, maybe instead of, you have some like symmetries of the property?
Can you be a bit more specific? I mean, just a symmetry property that...
maybe that it has some automorphisms that it satisfies.
Oh, this is actually a very good point. So in a subsequent work, which is not published yet, we actually heavily used symmetry properties of graph properties. So using different techniques, you can understand those graphs in the homomorphism linear combination much better if you have symmetry properties. So yeah, this is a very good point, and we are doing that at the moment, actually.
Oh, okay, I see. Are there other questions? So I think that is the last talk of the session. So thanks so much to all of the speakers, and hope to see you all again soon.